Hello, I'm going to explain why the sharing of the 960 to 1164 MHz band is such a sensitive subject for civil aviation. First, I will explain the concept of communication, navigation, surveillance, CNS, which is the keystone of aviation safety. Depending on the situation, we use different means of communication. The main means of voice communications at the moment is VHF in the 118 to 137 MHz band, which is very heavily congested in Europe. The higher part of the band has some channels dedicated to data communications called VDL Mode 2, but in very insufficient quantity. SATCOM voice and data for oceanic flights or remote areas, and soon SATCOM data in the European continent with the IRIS project. HF is still used for oceanic flight and in remote areas. ICAO is planning to deploy LDACs in the mid-2020s in the 960 to 1164 MHz band to meet the growing need for ground-air data exchange. The control command for certified and specific categories of drones requiring a C2 safety link will be able to operate perennially for the long term in the 5030 to 5091 MHz band for satellite links or terrestrial. The 960 to 1164 MHz band, meanwhile, can be used at low altitudes up until the LDACs is deployed in the corresponding airspaces. The en route navigation is based on three systems: GNSS based on GPS, augmentation systems like EGNOS, DME, VOR-DME, which allows to know the azimuth and the distance of a given station. The approach navigation uses different systems that make up the ILS, Instrument Landing System, including the DME that allows the pilot to know exactly the distance that separates him from touchdown. Sometimes surveillance techniques are used or supplemented for navigation applications. It's the case for ADS-B, which allows aircraft to monitor in real time the position of aircrafts equipped with a transponder at 1090 or 978 MHz. It's also the case for TCAS, ACAS, which is the last line of defense to avoid air collision between two aircraft. The TCAS gives climb or descent orders to the different pilots. Surveillance is carried out by different systems depending on the situation. For oceanic zones or remote areas, we use position reporting via SATCOM. For non-collaborative aircrafts, we use primary radars in the S-band for the coverage of final approach zones and in the L-band for wider coverage areas. The future needs in terms of UAV surveillance and the congestion of the 1090 MHz frequency make many European countries interested in the UAT at 978 MHz used in North America for general aviation surveillance. Collaborative-based surveillance at 1030 and 1090 MHz with the Space ADS-B from WRC 15 or Ground ADS-B at 1090 MHz, which retrieves the position report included in some messages, with the secondary radar, with WAM using the multilateration TDOA technique to cover large areas where a radar could not be used, such as mountainous areas. MLAT using the same technology as the WAM, but to cover smaller areas such as traffic over aerodrome or the short final approaches. Some countries think that the problem of audio PMSE in the 960 to 1164 MHz band is the same as the one of the video PMSE in the 2.7 to 2.9 GHz band, whereas it's a completely different issue. In this table, you will find the list of aeronautical systems using these two bands. In this table, you find the systems used by the air traffic control as part of the ATM, air traffic management. In this table, you'll find the systems used by the aircraft. You will notice that no embedded system uses the 2.7 to 2.9 GHz band. In this table, you find the systems used by the pilot. you will notice that the pilot does not use the 2.7 to 2.9 GHz band. In this table, you find the future systems to be used by the pilots. You will notice that the 960 to 1164 MHz band will be increasingly used by the crew. Statistical study of air crashes. You will notice that the majority of incidents occur when the pilot's occupancy rate is high, especially during the final approach phase. This table shows that the pilot's share of responsibility in air crashes remains almost constant over the decades. Fatigue is the major cause of accidents. But in fact, all the incidents are due to an accumulation of events without which the incident would not have occurred. The analysis of an incident through the plates of reason perfectly illustrates this observation. An external event may have an impact on the pilot layer, as by example, an increase in stress, a lack of concentration, or an increase in the decision-making time. Ultimately, for the record, no interference in the 2.7 to 2.9 GHz band will have any impact on the pilot layer, while an interference on the 960 to 1164 MHz band will have an impact. The same for future systems. The use of the 960 to 1164 MHz band. These are the different types of aircrafts: drones, general aviation, business aviation, commercial aviation. Here, the different systems using the frequency band. The 978 MHz UAT is strongly envisaged for general aviation and UAV surveillance in traffic areas. The WAM and the MLAT at 1030 MHz ground to air and 1090 MHz air to ground for surveillance in difficult areas. ADS-B at 1090 MHz and space ADS-B for other areas not covered with secondary surveillance radar. The DME and TACAN for DME-DME navigation. I would point out that from a civil aircraft perspective, a TACAN is equivalent to a DME. The secondary radar interrogating at 1030 MHz and waiting for a response from the aircraft at 1090 MHz. The TCAS-ACAS, which is the last line of defense to avoid collision. What would happen in the case of interference on the 960 to 1164 band? First, let's deal with the case of the frequencies 1090 MHz and 1030 MHz. These two frequencies are the keystones of surveillance, and any interference would have a direct and immediate impact on the pilot and the air traffic control, immediately endangering many lives. These two frequencies are considered as a sanctuary by civil aviation. What would happen if there is an interference on a DME? Let's consider a scenario where an aircraft interrogates a DME channel 100Y at the frequency 1124 MHz. The DME will respond on 1061 MHz. Let's take an interferer on 1124 MHz. Even if the interferer is located closely to the DME, he may continue to communicate without realizing that he is interfering. On the other hand, the DME will not hear the interrogations of the aircraft and therefore will not answer. Up until a certain level of interference is reached, the DME will not even realize that it is being scrambled. The pilot will only conclude that the DME is out of order. The same thing for an 1161 MHz interferer close to an aircraft. This example highlights several problems. DME responses at 1061 MHz will have no effects on the interferer transmitting at 1124 MHz. Airplane interrogations will have no effect on an interferer transmitting at 1061 MHz. The interferer can scramble without realizing it. The DME can become deaf to interrogations from the most distant aircraft without realizing it. The aircraft will not hear DME responses and the pilot will suspect that the DME is out of service. This type of incidents occur mostly when the aircraft is close to the ground, that is to say, during the takeoff and landing phases, during which the crew is subject to high levels of stress. At those moments, the priority of a pilot is not to report incidents, but to remain focused to the maximum to continue flying even under degraded conditions. For an interfered with aircraft flying at an altitude of 300 meters, the radio horizon is 72 kilometers, which means that the interferer to identify could be anywhere on a surface of 16,000 kilometers square. How can one imagine being able to identify and stop this interferer within an acceptable time frame? In the risk analysis, any impact on the pilot's environment is considered highly accident prone. The 960 to 1164 MHz band has a direct impact in the pilot's environment. Sharing in this band requires a long and thorough risk analysis. For a sharing scheme to be acceptable, important means of mitigation will have to be implemented to avoid any impact on the pilot's environment.